Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to discuss trusses having thermal changes and fabrication error analysis using stiffness method. Okay, thermal changes or temperature changes in truss and fabrication error. These two effect is actually bring the Q naught equivalent nodal forces for truss. Okay, so if before this, we will consider equivalent nodal forces in beam whenever beam is loaded by uniformly distributed load, which is subjected along the member or element, or the beam, okay, or the element is loaded with point load on the member, not at the end of the member, but at anywhere on the member. Okay, so all those, okay, effect means that a member when it is member when it is subjected by loading, member, not joint, because joint, uh, if the loading, if loading is subjected directly at nodes, it is Q. It is Q. Whenever member have loaded, okay, member or element has loaded. Okay, for example, if we have UDL, in beam we have UDL along the member, so it is Q naught, not Q. Whenever the member is loaded by point load at the center or at anywhere on the member, it is Q naught, equivalent nodal force. Because a member cannot carry load, we have to distribute to the node. Whenever we distribute to the nodes, so we call it as equivalent nodal forces. Okay, but okay, we haven't discussed yet Q naught in truss. Okay, now let's see together Q naught in truss. Okay, it is under uh, thermal changes and fabrication error, the effect that we need to consider whenever these two information, either one or both, is given in the question, thermal changes and fabrication error. Because whenever, for example, okay, try to understand like this. Thermal changes, bila dia effect, okay, it affect the whole, not only joint, the whole. Means that when we need to consider, okay, thermal changes means that uh, at all structure or element get the effect, not only joint. So it is just like the member get the effect or element get the effect. That's why it is under Q naught. It is under Q naught, not Q. So same goes to fabrication error. Same goes to fabrication error, because fabrication error is like this. Whenever the member or element is fabricated, dia tak sebut join. Join 1 or join 2. It is member A, member 1 or element 1 is fabricated. Okay, clearly mention about member. Member 1 is fabricated. Member 2 is fabricated. Okay, or member 1 or element 1 having temperature changes, member. Okay, so all these members get effect from either thermal changes or fabrication error. Okay, we have to understand that this is also Q naught. Okay, this is also Q naught. Means that we need to distribute forces. Okay, distribute forces to nodes. Because member cannot carry load. Just remember, member cannot carry load. So we have to distribute to the nodes. Okay, we have to distribute to the nodes. So whenever we distribute to the nodes, we call it as equivalent nodal forces. Equivalent nodal forces. Okay, let's see together. Okay, let's go to this Okay, if some of the member of the truss are subjected to an increase or decrease in length due to thermal changes or fabrication errors, then it is necessary to use the method of superposition to obtain the solution. This requires three steps. Okay, first, fix and forces necessary to prevent movement of the nodes as caused by temperature or fabrication, 1 and 2, and or. Okay, are calculated. Second, the equal but opposite forces are placed on the truss at the nodes and the displacement of the nodes are calculated using matrix analysis. Finally, the actual forces in the members and the reaction on the truss are determined by superposing these two results. This procedure, of course, is only necessary if the truss is statically indeterminate. If the truss is statically determinate, the displacement at the nodes can be found by this method. However, the temperature changes and fabrication error will not affect reaction and member forces since the truss is free to adjust to these changes of length. Okay, so let's see the formula. Okay, we jump through the formula for stiffness method. Okay, this is the formula. Okay, this is the formula. Because truss, remember truss has four degree of freedom per element. 4 degree of freedom per element. Two at node, two at near node, two at far node. So we have 4. Okay, this is actually the formula. Okay, so label here same goes to what we have done in beam. So ada label kat sini kan 1, 2, 3, 4. Remember? Okay, label ni akan follow label pada K. If we have K1, which is equivalent to 1, 2, 3, 4. So this one also got the same label. If the label is 3, 4, 1, 2, so it is 3, 4, 1, 2. So this is the formula considering temperature changes. Where alpha, we have alpha here. Okay, alpha is equal to coefficient of thermal expansion. We have discussed this in flexibility method as well. Coefficient of thermal expansion, and we have delta T. Delta T is the temperature. Okay, temperature, because temperature has degree Celsius, right? And alpha is per degree Celsius. So this will be cancelled. Okay, will be cancelled. So this is actually the formula that we are going to use. This for temperature changes. Okay, for fabrication error, this is the formula. Okay, this is the formula. This is Q naught. Okay, Q naught for element. Okay, Q naught for element. We have to do it one by one element. For example, if we have K, for example, if we have K2, which the label is 5612, then we will have this as 5612. Same to what we have done in beam. So for equivalent element nodal forces, because we have to do element by element first, then only we have to combine to get the equivalent nodal forces. We get equivalent nodal forces from equivalent element nodal forces. So this is the formula that we are going to consider. Okay, we are going to consider. So we have to have this additional to the stiffness equation. We have to put Q naught. Okay, Q naught whenever we have the effect of temperature and fabrication error. Okay. So don't worry. So we go through the example. So I want to brief this first before I will show to you how we analyze effect of temperature changes and fabrication error based on the previous video that I have made to you last week. Okay, so the question is determine forces in member. Determine forces in member 1 and 2. Member 1 and 2. Okay, 1 and 2. 1 and 2. If member 2 was made 0.01, too short. This is fabrication error. Okay, too short before it was fitted into place. Okay, so now what we need to do is we need to consider Q is equal to KD plus Q naught. So we have to do as usual, start with element global stiffness matrices. So we will get K1, K1, K1 we get label 3412, 3412, and then K2 we get K2 we get 1256, 1256, and K3, so we will get K3 we get 7812. So here is 7812. Okay, member 2, only member 2 get affected. Okay, member 2. Member 2 was made 0.012 short. Only member 2. So member 1 and member 3, okay, does not get the effect for this question. So what we need to do is, like this. Okay, so we will actually get this. Q1 node for element number 1, and for element number 1 it is K1, label for K1 3412, it is 3412, which all value equal to 0 because the effect is only for member number 2. So okay, so same thing goes to Q3 naught. Q3 naught. Okay, this is for element, yeah, equivalent element nodal forces. So we have this also. The value are 0. So the label 7812. We have 7812. And we have, okay, Q2 naught, which is equivalent to, okay, the formula is AE delta L over L, and inside this matrix is actually CX, CY, negative CX, negative CY, based on the formula. Based on the formula. It is AE delta L over L. Delta L is in unit meter, L in unit meter, so this will be cancelled. Okay, lambda X, lambda Y or CX, CY has no unit. Okay, this no unit. Okay, AE unit AE is kilonewton, and this is force. So unit must be in kilonewton. So we have AE, okay, AE here, and this will give the values in unit kilonewton. Okay, so we have CX, CY, negative CX, negative CY. Okay, CX, CY, negative CX, negative CY. So we have here CX or lambda X for member 2, this one. Okay, negative 0.8, negative 0.6. So we have here negative 0. Negative 0.8, negative 0.6, 0.8, 0.6. So we get, okay, AE, delta L, we have 0.01, too short. So too short is negative, negative 0.01. L for element number 2 is 5 meter over 5. Negative 0.8, negative 0.6, 0.8, 0.6. So this we get in terms of AE. In terms of AE, we get 0.01 divided by 5 times 0.8. So we get 0.0016. It is 0.0016. Okay. It is 0.01 divided by 5 times 0.6. It is 0.0012. 0.0012. Because it is negative. So here is 0.0016, negative 0.0012. Okay. And we should label this as 1, 2, 5, 6. So this should be 1, 2, 5, 6. So since in this diagram we have 8 by 8, 8 DOF representing 8 by 8, 8 matrix X, 8. It is 8 position. Okay, so we have Q equivalent, where we know that Q naught is equivalent to Q1 plus Q2 plus Q3. Naught is labeled for equivalent nodal forces. So what we get is like this. We have 8, right? All is 8 plus another 8 value plus, actually you can total it directly. Don't need to do this. This is just to show you step by step. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the procedure, but actually you don't need to do it like this. Okay, straight away give the Q naught value. 1, 2, 3, 4, 5, 6, 7, 8. So for Q1 naught, all 0 value. All 0. 0, 0, 0, 0, 0, 0, 0, 0. Same goes to Q3 naught. 1, 2, 3, 4, 5, 6, 7, 8. And we have the value for, okay, for Q2 naught at position 1, it is 0.0016. 0.0016. At position 2, we have 0.0012, 0012. And for position 5 and 6, negative 0.0016, negative 0.00012. This is 0000. So from this, okay, from this we get Q, this is Q naught. So Q naught is equivalent to, okay, this one. Okay, 0.01600. Okay, it is 0.001200, negative 0.016, negative 0.01200. It is 1, 1, 2, 3, 4, 5, 6, 7, 8. Oh. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so then only you have to substitute into full equation. Into full equation. Okay, the full equation is Q is equal to KD plus Q naught. Okay, so we will get Q is equal to KD okay plus Q naught, but without support settlement, And from this, we know that we only have 2 degree of freedom for unconstrained system. So we have, and there's no Q naught value, there's no Q value. There's no Q value here. So we just need to consider this. We just need to consider this. 2. Okay, up to 2 only. 1, 1, 2. 1, 2, 1, 2, 1, 2. Okay, so we just need to consider like this. So it is 0, 0 equal to AE. So K value. Okay, this is the K value. This K value. 0.378, 0.096, 0.405, 0.378. So it is 0.3378, 378, 0.096, 0.096, 0.405. Okay, times with D1 and D2 plus with, okay, plus with Q naught. Okay, it is okay, AE 0.0016 and 0.0012. Okay, so AE, or okay, just like this, we have AE here. It is 0.378, 0.096, 0.405 times D1 and D2 equal to AE negative 0. It is 0 minus negative 0 minus 0.0016, 0016 and 0.0012. So from here we can cancel this. So we put the value in the calculator. So we choose equation with 2 unknown. A1 is 0.378, A2 is B1 is 0.096, and then C1 is negative 0.0016, A2 is 0.096, B2 is 0.405, and then C2 is negative 0.0012. So we get D1 and D2 equal to 3.7 negative 3.7 times 10 negative 3 and negative 2.1 times 10 negative 3 as well. Okay, so this is in meter. It is 0.00 lah. 0037, 0.0021. Okay, so this is the D value. Okay, D value. And to answer this question, the question asks us to calculate the force in member 1. Force in member 1. So to calculate force in member 1, we have to use formula Q1. Q1 represent force in member 1. Q1 not represent equivalent element nodal force. This is different thing. Okay, so member force, member force. So member force formula for to calculate member force is AE over L negative CX, negative CY, CX, CY times with displacement. Okay, of displacement. Okay, remember that the label for this must follow the label for K1. K1 we label as 3412, 3412, and we have to, okay, this one. Okay, this is the thing lah. Okay, so for member 1, lambda or Cx is equal to 0, and then 1, length is 3 meter, AE is this. Okay, so we just substitute into the formula. I just wrote, this is the formula. Okay. Okay, then we will get this value. Okay, we will get this value. Okay, this is for member force, and we will do the same for member 2, So, but for member 2, since we have here, okay, the effect, okay, the fabrication error, this is AE, this is actually AE delta L over L. Okay, then we will get the value. Okay, so this is how we analyze or consider effect of fabrication error. Actually, for temperature changes, we need to do the same except the formula to calculate the equivalent element of the forces will be different. So this is how we calculate. Okay, so whenever truss got the effect of temperature changes and fabrication error, we need to understand that, okay, the displacement in structures, okay, may due to not only external load, but if the structure got the effect of temperature or fabrication error, so these three factors will influence the displacement. Even though in this truss there's no external loading, but due to fabrication error, okay, we still got the displacement value, because displacement, okay, displacement will be influenced by either external loading or effect of temperature changes as well as fabrication error. So that's why we get this the displacement for this truss. Even though the truss has no external loading, we still got the value of displacement. So this is how we analyze. And remember the effect of temperature changes and fabrication error, because in the truss there's no UDL. In the truss, it is very seldom we got point load on the member. Okay, not like beam. But the Q naught or equivalent element nodal forces in truss may come from temperature changes or fabrication error, because these two, temperature and fabrication error, will affect members. Okay, members. So it is just like member get the effect, get forces. Okay, so whenever member get the effect, okay, member get the effect, not join, not nodes. Okay, member get the effect from temperature changes and fabrication error, because logically kita tak dia tak ada join je yang get the effect. It must be member, it must be structure. Actually the real kalau for fabrication error, memang for element get the effect. Tapi kalau temperature changes ni, logiknya the whole structure we get the effect. Okay, but for analysis purpose, maybe in the question you can see that for temperature changes, member 1 get temperature changes like this, member 2 got temperature like this, but in reactive condition, if the effect come from temperature changes, it will affect the whole structure. But for fabrication error, we can pick certain element only, certain like this, certain element only to see the effect. Okay. So please remember, for fabrication error and temperature changer, using stiffness matrix method, okay, for the analysis in order to calculate displacement, okay, we have to consider these temperature changes and fabrication error as equivalent nodal forces. And we have to calculate element by element, means we have to calculate equivalent element nodal forces. Then only we combine to have element equivalent nodal forces Q naught. And then we have to apply back into stiffness equation. We plus Q naught. Okay, we plus Q naught, and then we solve for the displacement. And from the displacement, we can calculate either reaction at the support, or we can directly calculate member forces like what we have discussed just now. Okay, so that's all for discussion about the effect of temperature changes and fabrication error in truss analysis, in indeterminate truss using stiffness matrix method. So that's all. Thank you very much. We'll meet again in the next video. Assalamualaikum warahmatullahi wabarakatuh.